Welcome back. This is section 4 of lesson 2 of Introduction to Lens Design. And again, this week we're going to look at more of the mathematics behind some of the paraxial properties we've talked about last week and previously this week. So let's start with the power definition. The power of a surface is related to the change in index at an optical boundary divided by the radius of curvature at that boundary, or the change in index times the curvature. As I've mentioned previously, typically when we're doing the calculations we use curvature because multiplying by 0 isn't a problem. If we have an infinite radius and effectively are dividing by infinity or dividing by 0, we reach problems in doing the math. So typically for doing the calculations we'll use curvature, even though most of us tend to think in terms of radius. And again, in air, the power is equal to 1 over the effective focal length, 1 simply because that's the index of air. If we had a surface not in air, it would be equal to that index divided by the effective focal length. What the power tells us, basically, is how strongly incident rays parallel to the surface are going to be bent. So in this first example, what we see is a planar surface. Planar surface has 0 power, an infinite radius of curvature, and we see that the rays do not refract at all. The shorter the focal length, the greater the power, and therefore the more bending occurs as the rays interact at that surface. So let's consider a system with two thin lenses or two optical spaces. It's up to you how you want to think about it right now. But we have two powers, phi1 and phi2. They are separated by some distance t. The system is in air, so the object space index and the index space index are both equal to 1. The powered components, the powered faces, the thin lenses, are separated again by some distance t in some index n. And what we'd like to do is determine what the effective focal length is, but since that's measured relative to the principal planes, we sort of have to identify how to find the principal planes, and we want to find out the total system power for this system. We've talked about this. I've presented the equation previously. Now we're going to look a little bit at the math, and you'll notice we have our parallel rays coming in, so the initial slope is 0. At the point of intersection, the rays refract, so the slope angle changes, but exactly at that point the height stays the same. So when this ray refracts into this media, it has a new slope of u1 prime, but because we have a constant index, when the ray intersects this component here at an angle, a slope of u2, this u2 is the same as this u1 prime. Okay? Just has a difference in height because we've propagated through a material. After the refraction, it propagates at a new slope, u2 prime, and all of the rays converge to an image at the paraxial focal point in this particular case. Okay? So let's take a look at a little bit of the math. And again, we're going to start from the object, in this case an object from infinity. Those rays interact with the first powered component, and it forms an image. That image then serves as the object for the next optical component, which forms an image. I mean, in this particular case, that's all there is, but in a more complicated system, we'd use that new image to form the new object for the next component that forms a new image, etc., 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 through all of the surfaces within the system. And we're going to start with our paraxial ray trace equations. Again, as a ray propagates paraxially, one of two things happen. It interacts an index boundary, so it changes its slope, the direction of travel, or it's propagating through a constant indexed region where it's changing its height but keeping its slope angle the same. So if we go to the first boundary where we interact with the surface of phi1, we'll simply apply this equation, but we know that u0 is 0, so we can throw out this term. So u1 prime is simply minus y1 phi1 divided by the index in the after the refraction, which was defined as n on the previous page. And of course, this is equal to, when we want to calculate, the slope angle in image space, we'll apply the same equation. We now know what u2 is, so we can substitute, and then minus y2 phi2. Now what is y2? Well, the second height is equal to the initial height times the index times the angle that the ray travels in that media times the thickness over the index, and again just basically a little bit of algebra to try to pull some common terms together. And we can see that based on our paraxial definitions, the slope angle in image space times the focal length gives us our first height. Okay, remember our principal planes are planes of unit magnification, so the height of the ray at the principal plane is the same as the height that the ray was when it came in, which was that y1. So this tells us u2 prime is a function of the initial height times the total system power, which is again still one of our unknowns. So if we put all of this together, again simply substituting what we've already calculated and bringing it together in a nice form, using only those parameters that we know or have been provided, we can see that the power of our system is simply the sum of the individual powers minus the product of the powers times the thickness divided by the index. And that, of course, is still equal to 1 for in air over the effective focal length. So this shows mathematically how to derive that power equation that we talked about last week. We can also apply this to another simple case with two thin lenses. And again, whether we talk about power or inverse focal length, we can set up the same basic equation. So depending upon the information you've been provided, you may choose to solve the power equation in terms of power or focal length, but either way, it ends up with the same result. So let's talk about a couple of specific instances. And the first one I want to talk about is what's referred to as a Petzval lens. Petzval lens we're going to talk about more as we actually get our hands on doing optical design, and I promise that's coming. Next week's lectures will all be about getting your hands on Zemax, so it is coming. But the Petzval lens is important in that it's one of the first really designed photographic lenses. In other words, its behavior was actually calculated rather than effectively assumed. The Petzval lens and the Cooke triplet that I've talked about several times are two very important optical designs in photographic lens history, and we will spend some good time talking about them. When we talk about the Petzval lens, typically it actually consists of two sets of doublets rather than singlets. But remember, with our thin lens equivalent, we can treat any lens as a thin lens, and then we can treat any pair of thin lenses as a thin lens. So we're just, in terms of a thin lens equivalent, we're going to set up the system like this. And the properties of the Petzval lens are simply that the power of the two component groups are such that the power of the second group is actually, let me rephrase, the focal length of the second group is actually equal to the focal length of the system as a whole. The focal length of the first group is equal to twice the focal length of the system as a whole. Okay? And the separation between the two thin lenses is also equal to the system focal length. And if you go through the math, we simply see that we substitute for the various focal lengths and for the thickness, and we can see that 1 over the focal length is equal to 1 over the focal length, so obviously that works. And As I said, the Petzval lens is a very important photographic element, and we will spend lots of time talking about that as we proceed. Another important lens that we'll talk about is what's called the telephoto lens. And this is a system of lenses where the length of the system is much shorter than the actual focal length. So in this particular case, what we have are two lens groups, which again we're going to treat as thin lenses. I have a positive front group and a negative back group. And again, we have our standard power equation. If you are familiar at all with telescopes, the telephoto lens can be considered almost like the refractive equivalent to a Cassegrain telescope. But in this particular case, the front group I've set up with a focal length of about 100 millimeters. Second group has a focal length of about 55.5 millimeters. And I've adjusted the spacing between them to be 11, 12, 13, 14, 15, and 20 millimeters. And you can see that I have a significant change in focal lengths for this system simply by making these very, very slight adjustments to the lens spacings. So although my total system thickness only varies by about 9 millimeters, my focal lengths vary from almost by a factor of 6 just by making that slight change. Alright, so that concludes this section of Lesson 2, and I will continue again shortly. Thank you.